Good evening, everyone, and thank you for joining us for this live stream presentation, What Can We Learn from Star Clusters with Galen Gisler. I'm Laura Marcelia with Pajarito Environmental Education Center, otherwise known as PEEC, located in Los Alamos, New Mexico. I'll be the moderator for today's talk. Tonight's talk is being recorded. We're able to offer programming at this time because of our wonderful members and donors, so we'd like to thank you for your continuing support. Galen Gisler was born in Clovis, New Mexico, and graduated from high school there. With a PhD in astrophysics from the University of Cambridge, he eventually came to Los Alamos, where he worked at the lab for 25 years. Then he and his wife Susan moved to Norway, where he learned not quite enough geology at the University of Oslo, finally retiring back to their cozy mountain town. The PEEC Planetarium is his favorite place to spend time, and he's always eager to get back to it when this time of isolation is over. And with that, Galen, take it away.
Thank you very much for that, Laura. Appreciate the introduction, and I appreciate people tuning in this evening to hear my talk on star clusters. So what do we learn from star clusters? In the first place, they're things of great beauty, beautiful to look at. You can catch a few of them with your naked eye, but for muted. Even better, of course, would be a telescope if you have access to one. And when we're eventually able to resume dark night star parties, why don't you walk up to one of the telescope groups and ask to see some of these beauties? Of course, we all have access via the internet to photographs taken by very large telescopes on Earth or in space. Some star clusters have been known for thousands of years, at least as fuzzy spots or clouds, since ancient Babylonians and Greeks and other cultures turned their eyes toward the heavens. But over the last 2 centuries, with the development of precision measuring instruments, photography, and spectroscopy, star clusters have taught us a great deal about how our world is built, how stars live out their lives and die, and how old our universe is. Clusters of stars are our first stepping stones into the greater cosmos. We're going to be looking at some pretty pictures of star clusters first, and then we'll talk about what we can learn from them. Paul Arendt pointed out the Pleiades last week. They're easily visible in our winter sky with your naked eye. You follow the belt stars of Orion to the upper right, past the bright star Aldebaran, and there you land on this little cloud of stars, a kind of micro dipper. If you can count 7 stars, you have very good eyesight. If you count 20 or more, you're looking through binoculars. In fact, there are hundreds of Pleiades stars visible in telescopes. The blue clouds in this picture are dust and gas reflecting the light of the hot blue stars. Number 7 in Messier's catalog of cloud-like objects, or nebulae, was noted as a cloudy star by the 2nd century AD astronomer Ptolemy. You'll hear more about Messier's catalog in Didier Samon's talk on February 26th. M7 is visible in our summer sky just a little to the left of the Stinger stars in the constellation Scorpius. In this picture, notice the dense concentration of background stars and how the background stars appear to be redder and fewer near the cluster's center. From this observation, we know that the cluster contains substantial amounts of gas and dust, obscuring the background stars and causing them to appear redder than they actually are, just as the sun looks redder at sunset, especially when there's a lot of smoke or dust in the air. M13 is just visible to the naked eye, like a slightly fuzzy star in the summertime constellation Hercules, high overhead. In contrast to the 2 open clusters we've just seen, this is a globular cluster. It has vastly more stars and has a regular morphology, what we would call a relaxed morphology, densest in the middle and trailing off in all directions uniformly. Unlike the open clusters, this globular cluster shows very little sign of gas or dust within or around it. Now we'll take a tour of a few more open clusters and point out some similarities and differences. We've already seen the Pleiades and M7 here, and this one is a beautiful open cluster that was on my title slide. It's called NGC 299. Those initials stand for New General Catalog of Nebulae and Clusters of Stars, compiled by John Dreyer way back in 1888. This cluster is located within the Small Magellanic Cloud in the southern constellation of Tucana. So unfortunately, we can't see it from our latitude. The brightest star in this picture is red, but there are lots of bright blue stars as well. And the patchy distribution of background stars within the Small Magellanic Cloud, tells us that there's plenty of gas and dust associated with this cluster. The Jewel Box cluster, NGC 4755, is another southern cluster located in the constellation Crux, the Southern Cross. In this cluster, the brightest stars are blue, but there's at least one bright, brilliant red star as well. If you look carefully, you might notice rivers of darkness threading their way between the cluster stars, with some faint reddish stars poking through that darkness. Again, obscuration by gas and dust. A bit to the left of the bright star Sirius, which dominates our winter skies, are two clusters, M46 and M47. I'm showing here the cluster M47. These are in the constellation Puppis, the neighboring constellation to Canis Major. Bright red and blue stars dominate the cluster, and this is located in a dense part of the Milky Way. And again, we see an uneven distribution of background stars caused by absorption due to gas and dust within the cluster. If we were in the planetarium, I'd probably make you dizzy wheeling the dome around to look at some of these clusters. So maybe it's better doing this on Zoom, actually. In the northern sky of summer and autumn, and a favorite of amateur astronomers is what's known as the double cluster, or H and Chi Persei. It's easy to find using the bright star Murphak and the ghostly variable Algol in the constellation Perseus. This is also in a dense part of the Milky Way, and the field shows thousands of background stars, but virtually all of the brighter stars in this picture are members of these two clusters. They have separate designations. This one on the right is called NGC 869, and this one on the left is NGC 884. But they're physically close to each other and likely have a common origin. The double cluster is visible to the naked eye and was first noted by Hipparchus in the 2nd century BC. Another naked eye cluster is in the constellation Cancer, M44, number 44 in Messier's catalog. It's sometimes called the beehive cluster, but a more ancient name for it is Praesepe, which is Latin for manger. Ptolemy noted this object as a cloud within the crab, the constellation of Cancer. It was called Praesepe because Romans saw this object, the cluster M44, as a manger from which two donkeys were eating. The donkeys are the two 4th magnitude stars, Acellus Borealis and Acellus Australis, to the north and south. The names of these stars mean northern ass and southern ass, respectively. Once again, the careful eye can discern regions where background stars are obscured and reddened. There's another beautiful cluster in Cancer, Messier number 67, which unfortunately is not a naked eye object. It lives high above the plane of our galaxy, unlike most open clusters, which live in the disk. You don't see a lot of background stars. The one bright star that you see at the upper left is a foreground star. We also don't see a lot of gas and dust or evidence for that. And we'll come back to this cluster later on. There are reasons for this. In the summer constellation Cygnus, very close to where the wings join the body, is the cluster Messier number 29, M29. This once again is in a crowded field of the Milky Way, and the patchy distribution of background stars is a telltale sign of obscuring gas and dust. Roughly equal numbers of bright red and blue stars adorn this cluster. And then we have the globular clusters, which are all very much more massive than the open clusters, and they show much less variety in terms of form and population. So what do we make of the diversity of open clusters and the uniformity of globular clusters? What do these aggregations of stars signify? And how can we use them to understand the nature of stars and the structure of our world? Think about the differences among them. Globular clusters appear relaxed, uniform in distribution from the center outward, where open clusters may have a few thousand stars. Globular clusters have hundreds of thousands of stars. Globular clusters also show no or much less evidence of gas and dust within. Finally, globular clusters are found mostly outside the plane of our galaxy, while open clusters are found within the disk. To round out the general picture of star clusters, I'll show a few pictures of what are called embedded clusters, in which the stars in the cluster are enveloped by glowing clouds of gas. This one is called R136 and is part of NGC 2070, which is in turn part of the Tarantula Nebula in the Large Magellanic Cloud, visible from the southern hemisphere. You may have seen this photograph. It was featured on the NASA site Astronomy Picture of the Day last Sunday. To the left of this bright cluster is a dark patch of obscuring dust, and then surrounding the whole are glowing clouds of gas. Hydrogen is diagnosed by the red color, oxygen by the green. One of our favorites in the summertime sky is Messier 16, the Eagle Nebula in Serpens, just above Sagittarius. In addition to the cluster of bright stars, we see glowing clouds of hydrogen gas and the iconic pillars of creation deep in its heart. I'll come back to this image later. And of course, our favorite in the wintertime sky is the great nebula in Orion, the little fuzzy feature in the sword hanging from Orion's belt. That fuzzy feature is easily visible to the naked eye, and it earned number 42 in Messier's catalog. Within this nebula is this tight cluster of 4 stars, which was first noticed by Galileo with his small telescope. Last week, Paul Arendt talked about double stars in this trapezium cluster. Cluster is much more apparent in the infrared image at the right, but the gas cloud surrounding it is seen in the visual view at the left. These embedded clusters, rich with gas and dust, apparently form one end of a continuum with globular clusters at the other end and open clusters in the middle. It seems that this continuum might represent age, with the embedded clusters representing the birth of star clusters from a gas-rich cloud, the open clusters being of intermediate age, and globular clusters being very old. We'll try to confirm that shortly, but we need more information first. When we come upon a grove of trees, we have no trouble in distinguishing which are young, which are older, and that different species live in close proximity to each other. Noticing the fallen remnants of some trees, we can likely piece together a sequence of events. And we can make return visits to see how things change over the years. We have no such luck in astronomy. We only have snapshots at particular moments in time, and we can't perform experiments. Our lifetimes are far too short to follow the changes in stellar clusters. We see stars all over the nighttime sky of different colors and brightness. Are faint stars faint because they're farther away or because they're intrinsically faint? Until we were able to measure the distances to stars, we couldn't tell. But clusters give us an advantage. When we see stars tightly grouped together on the sky, like the Pleiades here, we can assume that they are physically close together and thus at approximately the same distance from us. So at once we learn that some stars are intrinsically brighter than others. But we can learn more by probing a little deeper. The Danish astronomer Einar Hertzsprung and the American astronomer Henry Norris Russell independently came up with the idea of plotting the apparent brightness or magnitude of a star against a color index for stars in a cluster. Such plots are called Hertzsprung-Russell diagrams, after the names of their creators, or color magnitude diagrams. The color index of a star is found by measuring the brightness of the star in two different filters, blue and visual typically, and taking the difference. When you do this for the Pleiades, you get a diagonal line across the plot with only little scatter. The brightest stars are bluest, the dimmest stars are reddest. In case you're wondering, the B-V color index of our sun is about 0.6. The spectral types of the stars also vary continuously along this sequence, with the highest temperatures corresponding to the brightest and bluest stars. When this was done for other clusters, people realized that stars had a tendency to lie on similar lines in these diagrams for a number of clusters. You could then compare color magnitude diagrams for different clusters, and by comparing the apparent magnitude of stars at the same color along the main sequence, you could determine the relative distances of clusters. Since I've mentioned temperature with respect to the color of stars, I show here plots of what we call black body radiation, which is electromagnetic radiation emitted by an opaque body in thermal equilibrium. A cool body emits primarily in the infrared. As temperature is increased, the peak in the radiation shifts into the visible spectrum from red to yellow to blue, and finally to the ultraviolet. Our sun's surface temperature is a little higher than this. It's about 5,500 Kelvin. So its emission peaks here in the yellow-green part of the spectrum, giving us what we experience as white daylight. Stars are classified into spectral types by looking at the lines in their spectra. And the classification scheme was first developed by Wilhelmina Fleming, Antonia Maury, and Annie Jump Cannon, some of the famous women of the Harvard College Observatory in the early 20th century. The system was originally alphabetical, with A having the strongest hydrogen lines and M having the weakest. But it soon became apparent that arranging them in this sequence discovers a relation with temperature, where O stars are the hottest and bluest, and M stars are the coolest and reddest. Our sun with spectral type G is in the middle of the sequence. We've seen a color magnitude diagram for the Pleiades, and I'll show a composite color magnitude diagram for several open clusters later. But what about the globular clusters? There are many thousands more stars in globular clusters, but with enough patience, you could plot that color magnitude diagram and find something completely different. Instead of a continuous sequence from lower right to upper left, like you have in the Pleiades, this sequence is bent in the middle, shooting off to the upper right. The brightest stars in globular clusters are red, not blue. Still, the lower part, before the bend, beneath the bend, looks like the main sequence in the Pleiades, but perhaps with more scatter. The cluster is a lot more distant than the Pleiades, so the errors are larger. The stars above and to the left of the bend present a puzzle, which I think is not yet resolved. Spectral types here are indicated along the bottom, while the color index along the top. Remember, the sun is at about 0.6. There are no O-type stars in globular clusters, and what B-type stars there are not part of the main sequence. Making color magnitude diagrams for clusters of stars became an industry in the middle of the 20th century, and this work continues to the present day. Let's look once again at the open cluster M67 in Cancer. This cluster and another cluster called NGC 188 are extremely well studied, and their color magnitudes diagram look intermediate between those like the Pleiades and those of the globular clusters. There's a bend in the main sequence, but it's at bluer color or higher temperature, and there's a zigzag before it shoots off to the upper right. This Hertzsprung-Russell diagram is a color magnitude diagram in which absolute magnitude, that is corrected for the distance from the apparent magnitude, is plotted against temperature instead of apparent magnitude against color. But morphologically, the absolute magnitude temperature plots look very much like the color magnitude plots. Of course, in order to know what the absolute brightness of stars are, we need to know their distances. Which brings us to the illustration of parallax. The technique of using parallax to determine distances to earthly objects, a tower in the foreground of a range of hills, for example, has been known since antiquity. The first successful attempt to measure the distance to a star was made by the German mathematician Friedrich Bessel in 1838. Because the angles are very small, precise instruments are required, and only the nearest stars can be measured in this way. By 1900, only a few hundred stellar distances were known, and only a few thousand more were measured during most of the 20th century. With the launches of the astrometric satellites Hipparcos in 1989 and Gaia in 2013, we now have accurate distances to over 1 billion stars. The distance and proper motion data that were acquired by the Hipparcos and Gaia satellites are used by the software that we operate in the PEEC planetarium. So next time you visit, you can remember that. Using distances for the nearest stars and then sliding the main sequences of color magnitude diagrams up or down the absolute brightness scale so that they coincide, you can construct a composite Hertzsprung-Russell diagram for several open clusters. Clusters like NGC 2362 and the Perseus double cluster have many more bluer stars and a much bluer main sequence turnoff than clusters like NGC 752 and M67. This diagram is marked with ages from 10 to the 7th years to 10 to the 10th years. In a couple of slides, I'll address where those numbers come from, but basically, it's from another 20th century advance, knowing that stars shine by nuclear fusion, consuming the available fuel. Given the distances to all the stars in the catalog produced by the Hipparcos satellite, we can produce a universal Hertzsprung-Russell diagram for stars in our neighborhood. The four axes on this plot show different quantities that are correlated with one another. At the bottom is the color index, and at right, the absolute magnitude, corrected from the apparent magnitude by the known distance of each star. At top are both the spectral type and the temperature in Kelvin. And at left is the luminosity, calculated from the absolute magnitude and scaled to the sun's luminosity. It's an astonishing range in total luminosity, or equivalently power, energy expended per unit time. There are stars that are only 1/100,000th as bright as our sun, and other stars that are 100,000 times brighter. A total range of a factor of 10 billion, with our sun smack in the middle. I know of no other physical object or class of physical objects that have such a tremendous range in properties. Let's think a little bit about what this diagram means. On the right, we have red stars that are very bright and red stars that are very faint. How can this be? Think about glowing red balls of different sizes. The larger ones of the same color would be brighter. Likewise, on the left, we have some blue-white stars that are much fainter than other stars of the same color. So these must be much smaller. This naturally gives rise to the terminology red giants for stars in the upper right, and white dwarfs for stars in the lower left. The strong line running from upper left to lower right is called naturally the main sequence. The Roman numerals here are spectral classes of these various stars. So these are determined by looking at the spectra of their stars. The main sequence is all we see in very young clusters, like those embedded in their birth nebulae, while old clusters like M67 and the globule clusters populate the giant branch and other regions of this diagram. Sparsely populated areas in this diagram represent very brief spans of time in the overall lifetime of stars. Next week, Joyce Guzik will discuss some of these sparsely populated regions in her talk, Why Do Stars Pulsate? So come back for that. But what distinguishes stars along the main sequence? What makes some stars so much hotter and brighter than others? We can guess that it might be mass, that the hottest and brightest main sequence stars are much more massive than the cooler and fainter ones. But we need a little bit of physics to establish that fact. How can we measure the mass of a star? If the star is alone, we're out of luck. But if the star has planets or is a member of a binary system, we can use Kepler's laws. We watch the orbits of the planets or the orbits of the two stars about their common center of mass. From spectroscopy, we can measure their velocities. And if we know the distance, we know the physical separation between the stars. Then Kepler's laws enable us to determine their masses. If they are eclipsing binaries, we can also measure their physical sizes and the masses of the two components separately. So people make these measurements and they calculate these masses, and then they compile them in catalogs for reference. From one such catalog, I've plotted luminosity against mass for main sequence stars, showing an extremely tight correlation. Note that while luminosity in this diagram varies by over 7 orders of magnitude, mass varies by only a factor of 300. The most massive stars are very much brighter than the least massive ones. Here's a version of the Hertzsprung-Russell diagram with some particular stars in our neighborhood identified. Here's the bright red supergiant Betelgeuse in the shoulder of Orion. Here's the bright blue main sequence star Bellatrix in the other shoulder of Orion. Here's the blue supergiant Rigel in one of Orion's feet. And likewise, another blue supergiant is Deneb in the constellation of Cygnus. Masses along the main sequence are marked in violet, as calculated from the correlation on the previous slide. These faint diagonal lines are marked with the radius of stars that would have that luminosity at that temperature, based on a simple relationship between temperatures, brightness, and size of a black body. Then the lifetimes, marked in green along the main sequence, are easily calculated. Assuming a given fraction of the star's mass is hydrogen fuel in the core, the luminosity tells how fast that fuel is consumed. The luminosity, remember, is power, energy expended per unit time. And the quotient, mass, here in violet along the main sequence, divided by luminosity, gives a lifetime. So for example, a star like Spica with 10 times the mass of our sun, it's a lifetime of 10 to the 7th years. You divide the 10 solar masses by the luminosity 10,000 in solar units, you get 10 to the minus 3, which gives a lifetime, which is 1,000th, 10 to the minus 3 times the lifetime of our sun. So for the sun, the lifetime is 10 to 12 billion years, but for a 60 solar mass star, it can be only a few million years. Because the most massive stars are so much brighter, they burn through their fuel much faster than small stars do. The white dwarfs here at the bottom represent the endpoints of the lives of stars less than a few times the mass of our sun. We'll get back to that later. Beyond simply estimating how long it takes for a given star to burn up the hydrogen fuel in its core, theorists have been able to make detailed models of stars to show what happens subsequently and how the various regions of the Hertzsprung-Russell diagram are populated. In this diagram are plotted schematic computed evolutionary tracks of a sun-like star, a star of 5 solar masses, and a star of 10 solar masses. These tracks are marked with the phases of nuclear fusion that go on in the interior star during its passage along this track. In a talk that I'll give next month on the 12th of February, entitled "We Are Stardust," I'll discuss the synthesis of new chemical elements that occurs as stars live out their lives. Please come back again then. And come, I'll mention it again, to Joyce Guzik's talk next week, where you could learn how stars pulsate when they travel through these parts of the diagram. So in this frame, I've ordered 9 open clusters by their approximate ages, as well as they can be determined by today's techniques. Embedded clusters are younger than any of these. Indeed, they are still forming stars, so they're effectively age 0. The oldest open clusters we have found, like M67 and NGC 188, are not as old as our sun, but they're much younger than the globule clusters. So here we have a range of from 13 million years all the way up to 3.2 billion years, with the Pleiades looking kind of like a young cluster with all those blue stars, but not really as nearly as young as the Perseus double cluster or as M29 in Cygnus. And then for the globular clusters, here are their distances and ages for just a few of them. They're all much farther from us than the open clusters, since they all reside in the spherical halo of our galaxy, unlike the open clusters, which are roughly speaking in our neighborhood. Globular cluster ages determined by stellar evolution models vary from 11 billion years to upwards of 13 billion years. And these numbers put hard constraints on cosmological models of the origin of our universe, thought now to be just under 14 billion years old. So some of the globular clusters in our galaxy were formed less than 1 billion years after the Big Bang, apparently. Globular clusters differ systematically from open clusters in having lower abundance of metals, which is how we speak of elements heavier than helium, in the spectra of their stars. This is consistent with their having formed before substantial enrichment of the interstellar medium from supernovae, that is, early in the history of our universe. Globular clusters are distributed spherically about the center of our galaxy, while open clusters reside within the disk. According to present models of cosmological evolution, the halo was formed by concentrating dark matter in the center, and then globular clusters formed around that. The disk was formed later due to infall of gas from the intergalactic medium into this potential well, having some angular momentum and spinning around the galaxy's center. Stars in open clusters, stars in globular clusters, and stars in the general field show similar distributions over mass. There are very many small faint stars and very few massive bright stars. Various people have attempted to measure this mass distribution, starting with Edwin Salpeter in 1955, who came up with a power law. Massive stars are exceedingly rare, and low mass stars very common. That power law cannot extend indefinitely to low masses, or you'd end up with infinite mass of clusters. So various cutoffs or flattenings of the distribution have been proposed. At masses above 1 solar mass, the power law seems to be universal, and that seems to constrain models for star formation. The process of star formation from a large cloud of gas evidently results in this kind of distribution for stars in a cluster. When a very massive star forms, its radiation heats up the surrounding gas and quenches the formation of other massive stars in its neighborhood, while smaller stars can form, shielded in pockets of denser, cooler gas. We can in fact see that process in action. Let's look once again at the Eagle Nebula, M16 in Serpens, just above Sagittarius. And we're going to zoom in with the aid of the Hubble Space Telescope on those pillars of creation. Stars are forming throughout the entire Eagle Nebula. But in this region and other similar regions, our view is dominated by the dark clouds of molecular hydrogen and dust that form these pillars. The pillars are being evaporated by the ultraviolet radiation of hot young stars, some of which are outside this field, and others are obscured by the pillars themselves. If you look closely, you can see narrow little fingers projecting from the pillars. There's a bunch of them all over. These narrow fingers are shadows created by what's called evaporating gaseous globules, EGGs for short, eggs, a highly appropriate acronym. These eggs shelter new, smaller protostars that are forming within them. Not all of them succeed in forming new stars before evaporating completely, but many of them do. Star formation is a very messy process. At least it is these days. So the formation of open clusters is modulated by the ionizing radiation from nearby hot new stars, by shock waves from newly minted supernovae, and general turbulence in the interstellar medium. This results in the very wide variety of morphologies we see in today's open clusters. The formation of globular clusters early in the universe's history, when conditions were presumably less chaotic, it's possibly far more efficient in rapidly consuming all the available gas. The low abundance of heavy elements likely contributed to that efficiency. In this slide and the next two, I illustrate the life cycles of stars, showing examples from our neighborhood. Detail in a particular star's life will depend on whether it has companions, but we generally expect that stars of about 20 solar masses will end up following a red giant phase and a supernova explosion as neutron stars or black holes. Our sun and stars like our sun were likewise born in embedded clusters, and for some part of their lives were members of open clusters, many of which gradually dispersed. There have been attempts to identify other stars from our sun's birth cluster, but the results have so far been inconclusive. Erica Fogarty gave a talk about that project in our planetarium a couple of years ago and pointed out a few stars that might be siblings to our sun. We're not real sure. We have a pretty good idea of what will happen to the sun in the future, according to the theorists' models of stellar evolution. In about 5 billion years, the sun's outer layers will puff up and it will become a red giant. The outer layers can puff up so much that they might even engulf our Earth's orbit. For life on our planet to survive longer than that, we'll have to find a new home somewhere else in space. But fortunately, we've got a long time to plan that exodus. After the red giant phase, it will cast off much of its envelope, becoming a planetary nebula with a white dwarf at its center, like the companion to the bright star Sirius, Sirius B. Red dwarfs at the lower end of the main sequence are the most common stars, but because they're so faint, none are visible to the naked eye. 35 of the 46 stars within 15 light years are red dwarfs, and V577 Monocerotis is one of the best studied ones at 13 light years away. Because these stars have main sequence lifetimes much longer than the current age of the universe, we don't have any examples of their post-main sequence fates. So we really don't know how they will evolve, although we can and do construct models that give us hypothetical remnants from their evolution. Concluding my talk, here's a rough summary of what we have learned from globular clusters. First of all, they're pretty to look at. Lots of differences in morphology. We go from embedded clusters through open clusters to the very regular globular clusters. The stars range in colors and brightnesses, and the way they range systematically in colors and brightnesses can tell us a lot about their histories and their ages. We get distances to stars by parallax, and then we can just get distances to clusters by main sequence fitting. The color magnitude diagrams can teach us cluster ages. They can teach us about stellar evolution and about stellar lifetimes. Observing cluster formation in molecular clouds, such as in the Eagle Nebula, the Pillars of Creation, teaches us how stars formed via successive fragmentation, big stars, and quenching each other's formation, allowing smaller stars to form in these eggs, these encapsulated gaseous globules. And there's a chaotic environment throughout that area, leading to varied morphologies. Globular clusters formed very early and probably much more efficiently, although we don't know very much about that, because looking at the very early universe, we have to use very large telescopes looking very far away. And there are some tentative results now on the formation of some globular clusters, but we are poised to wait for better answers from perhaps the James Webb telescope, which hopefully will be launched later this year. I'll be glad to stick around to answer any questions.
Thank you so much, Galen. So let me look at what questions have come in so far. There's one from Edward Fitzgerald, which you may have already answered. Could the color spectrum graph of the stars be interpreted as a star's life cycle?
Hello, and can we show my video? There we are. Okay, right. So it's a good question. The color magnitude diagram of a cluster could possibly be used to, whoops, I don't want to go there. So there is a morphological similarity, if you will, between a color magnitude diagram of particular clusters and the evolutionary tracks, which are over here somewhere. But in order to compute theoretically a color magnitude diagram, what you have to do is take a whole bunch of evolutionary tracks of stars along the main sequence and put them together in a particular way called an isochrone, which then should, if the theory is right, mimic what we see in the color magnitude diagrams. None of these are perfect. I did some of this work a very long time ago. Joyce Guzik has done some more of this work more recently, and other people have too. Sorry, I'm trying to go back to the color magnitude diagrams. But no, I want to see this one. But basically, the game of that is to try to compute an isochrone that fits M67, and then you come up with the age for that cluster. The ages that are listed here on this diagram are the ages of stars that would just be leaving the main sequence at that time. So what we determine as the age of a cluster is the lifetime of the last star still left on the main sequence. I hope that answers the question. I may have made it more complicated than it really is.
Well, Edward says thank you, so it looks like you've done a good job.
Right.
Wendy says, thanks, Galen. Fantastic talk and lovely graphics. Complex but fascinating subject, well explained.
Oh, thanks.
Marilyn asks, what is the age distribution of stars in our galaxy?
Oh, very good question. Right, for our galaxy as a whole, I mean, we still have some bright new clusters forming, bright new stars forming all the time, basically, but star formation is slowing down, as time goes on, and so I would guess that the age distribution of stars in our galaxy is more similar to very old clusters, is dominated, I would say, by very old clusters like M67 and the globular clusters. Our sun is 6 billion years old or so, and M67, 3 and something billion years old. The globular clusters are up to 13 billion years old. I think it's really dominated by much older stars, especially, you know, when you look at the central bulge of our galaxy. In spiral arms, you see you know, predominantly more younger stars. That's where you have, you know, supernovae and star forming regions and all that sort of thing occurring. But globally, it's we're pretty old. Our galaxy is pretty old.
Cool. Let's find. Joyce asks, was the sun once part of an open cluster?
We think it was. We think that all stars were formed in clusters. You know, stars. I mean, stars form from clouds of gas, and these clouds form into stars by this process of fragmentation, with, you know, this whole spectrum of stars forming from, you know, a few very bright hot ones and a whole bunch of small faint ones. Clusters disperse over the years, and either because they come into gravitational contact with other clusters, or in the general gravitational field of our galaxy, as clusters move around, you know, the stars within them, they have their own significant proper motions within the cluster, and they gradually disperse. We can see that happening. The Hyades cluster, which I didn't show tonight, but I've showed it in other planetarium shows. We determined that it was a cluster because all the stars seem to be moving together across the sky. Their proper motions are aligned with each other. But there are small differences in those proper motions, and the cluster is gradually becoming larger and larger and larger, and in the end it will dissipate out into the interstellar medium. So as I said, Erica Fogarty tried to identify some of the stars from our birth cluster. You can look up actually solar siblings as a search term in Google. And you'll find a few stars that some people think might have been formed in the same cluster as our sun. But, you know, it's kind of a speculative exercise to do that. And, you know, people aren't going to agree on which stars actually belong to that birth cluster.
Interesting. Another question from Joyce. Do you have any ideas why M67 has hung together as a cluster for so long?
So I think it may be because it has an orbit about the galaxy that keeps it, or that takes it high above the galactic plane from time to time. Right now, it's at a galactic latitude of 30 degrees. NGC 188, which is even older, is even farther away from the galactic plane than M67. So the guess is that they have suffered fewer gravitational interactions with other clusters and other stars, and so that's enabled them to hang together as long as they have. There are not very many clusters in that category. M67, NGC 188 are the two oldest ones that we know about. There are a few others, but far more common are the much younger clusters in ranges of, you know, from a few million years up to 100, 200 million years old.
Cool. Question from Thomas. Please briefly discuss Kraken collisions.
I have no idea what he's talking about. Can he explain that
He
to
has
me?
it in quotes, Kraken.
Yeah, no, I don't know what those are. Kraken collisions. Yeah. I'll have to pass on that one. He stumped me. Kraken collisions. Kraken is a mythological character, isn't it? Or a dragon or something.
I'm not sure.
Can he? Oh, okay. All right. So I've just done a Google. previously unknown galactic collision between the Milky Way and the mysterious. Okay, all right, now I know. All right, yeah. So that's a collision between our galaxy and perhaps another galaxy that we're not really sure about, that it existed, but people have looked at distributions of these filaments, streamers of stars in our galaxy, and speculated that they resulted from a collision with another galaxy, which apparently is this Kraken. I don't know how solid that information is. I see that there are several. Google tells me that there are a whole bunch of reports on it from the last few months, and I'm sorry, I haven't kept up with that part of the science, so I can't offer any more details on that. Perhaps that will be something we can look up in the future and give another talk on at some point. Thanks for the idea.
Yeah, just to confirm, Joyce said the newfound Kraken merger may have been the biggest collision in Milky Way's history. So it seems like you're talking about the right thing.
Right. Mm-hmm.
So I don't see any other questions in the chat, but I had a couple that I wanted to ask.
Certainly.
So why is it that globular clusters are found outside of the plane of the galaxy?
So I think they were formed early enough that that the galaxy had not developed sufficient angular momentum for the disk population to develop. So the disk population developed later with stuff falling in, and as stuff falls in to this potential well that was formed by the dark matter that seeded the evolution of our galaxy. By some happenstance, it had sufficient angular momentum to make the thing as a whole rotate. This is all very speculative, but globular clusters formed in a fairly spherical distribution in that initial potential well that was created by the dark matter that seeded our galaxy, and so that's where they've stayed, basically, out there. I mean, they orbit around the center of the galaxy, and they pass through the plane of our galaxy from time to time. Some of them you can see right now are very close to the plane of our galaxy. Others are most of them are well outside the plane, but they do pass through the plane, and may have some effects resulting from that, both on themselves and on the distribution of stars within the plane of the galaxy itself.
Cool, thank you. And then my other question was, what are some good clusters to look at, like that are above the horizon right now?
Oh, above the horizon right now? Well, certainly the Pleiades. Yeah. Of course, the Orion Nebula is a wonderful thing to look at right now.
Yes.
If you so in the cluster, in the constellation of Auriga, which is a neighbor to Taurus and Gemini, just above Orion, there are between Gemini and Auriga, there's several clusters, and they're all in the range M35, M36, M37, M38, and they span a range of ages, and they're beautiful. I was actually thinking about showing them in this talk, but I basically ran out of things to show. But yeah, those are very nice clusters to look at right now.
Cool, thank you. So with that, there aren't any other questions in the chat. So Galen, thank you so much for your presentation tonight. That was really interesting. Thanks again for tuning in. Good night, everyone.
Thanks, and thank everybody for joining in.